Okay, today we're going to look at matrix identity and inverses. So let's begin with the identity of a matrix. So this is like the number 1 for a 2 by 2 matrix. We use I as 1, 0, 0, 1. Okay, and this is our identity matrix because when we multiply A times I, we have A. And this is the same as when we multiply I times A. Right? So in our analogy, 3 times 1 is equal to 1, which is 3, which is 1 times 3. So it's neutral. When you multiply by the number 1, it does nothing. Much like when you multiply a matrix A times the identity matrix, it gives you back the same matrix. Okay, so let's have a look at the identity of a 3 by 3 system. So for 3 by 3 matrices, the identity I is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and again we have A, I is equal to A, which is equal to IA. But of course you could multiply a matrix with 3 columns times I and say 4 rows, and you would hope to get back the matrix A, as you would. Right? However, if you reverse that, that would not be defined. Okay, so let's have a look at example 7.1. So we've got a matrix A equal to 6, 5, 5, 4, and I is the 2 by 2 identity matrix. Let's multiply A times I. So we've got 6, 5, 5, 4 times 1, 0, 0, 1. Alright, so remember we take the first row of the matrix on the left and match it up with the first column of the matrix on the right. Multiply those corresponding entries and add the result. So that's 6 times 1 is 6, plus 5 times 0 is 0. And then we take this first row and match it up with the second column of the matrix on the right. And so this time we have 6 times 0 is 0, plus 5 times 1 is 5. Okay, now that we've done that, we move down to the second row. We match that up with the first column. We have 5 times 1 is 5, plus 4 times 0 is 0. Next, we match this row up with the second column of the matrix on the right, and we have 5 times 0 is 0, plus 4 times 1 is 4. Okay, now we can simplify this, and we've got 6, 5, 5, 4. Alright, similarly, IA equals 1, 0, 0, 1 times 6, 5, 5, 4, which is 1, 0 times 6, 5 gives 6 plus 0. Then we have 1, 0 times 5, 4, which gives us 5 plus 0. Then we have 0 plus 5. And then we have 0 plus 4. Okay, simplifying that, we get the same thing, 6, 5, 5, 4. All right, let's move on. So the inverse of a matrix now this needs to be a square matrix in order for an inverse to exist. And even though it's square, the inverse may not exist. You need the determinant of the matrix to be non-zero for the matrix inverse to exist. So if det of A is not equal to 0, then A inverse exists such that A times A inverse gives the identity matrix, and that's also the same as A inverse times A. So this is analogous to, or similar to, 3 to the minus 1 being 1/3 is such that 3 times 1/3 is equal to 1. Right? Remember, this is neutral in multiplication. Now, our first claim, Theorem 5, if the inverse of a matrix exists, then it's unique. Okay, so say Theorem 5. If A inverse exists, then it's unique. Meaning there are not two of them. There's only one, right? Unique is unique. Alright, so let's prove this. So suppose B1 and B2 are both inverses of A. So we want to show that B1 has to be equal to B2. Right, so assuming that we've got two of them, they've got to be equal. Alright, so if they are inverses of A, then A times B1 would give I, which would be the same as B1 times A, and A times B2 would give I, which is the same as B2 times A. Alright, now let's have a look at this equation right here and multiply that on the left by B2. So multiplying by B2 in this one on the left, we have B2 times A times B1 is equal to B2 times I, which is B2 by definition of the identity matrix. Now multiplying the equation I equals B2A by B1 on the right, just taking this, we have B1 is equal to I times B1, which is B2A times B1. Okay, now notice B2A B1 is B2A B1. So we can compare these, right? So since those two are the same, and what that tells us is that B1 is equal to B2. B2 equals B1 from above, right? So we've shown that if we have two inverses of A, then those two inverses have to be equal, so there's really one. Alright, so hence the result is true, the inverse is unique. Okay, let's move on to an example 7.2. Which says, show that the matrix B is the inverse of the matrix A. So, minus 4, 5, 5, minus 6 is inverse of A, which is 6, 5, 5, 4. Okay, so all we really need to do is multiply these matrices together, both A times B and B times A, and show that we have the same result, the identity matrix. So AB is equal to 6, 5, 5, 4 multiplied by minus 4, 5, 5, minus 6, which is 6 times minus 4 is minus 24, plus 5 times 5 is 25, and then we have this row with this column, so 30 minus 30. Okay, now this row with this column gives minus 20 plus 20, and this row with this column gives 25 minus 24. Okay, now these differences give 1, 0, 0, and 1. So that's the identity matrix. Okay, so we've done the AB multiplication. Now let's move on to the BA multiplication and show that we also get the identity matrix. So B times A is minus 4, 5, 5, minus 6 times 6, 5, 5, 4, which is, okay, this row times this column gives us minus 24 plus 25. Then this row times this column gives us minus 20 plus 20. This row times this column gives us 30 minus 30. This row times this column gives us 25 minus 24. And again, this is the identity matrix. Okay, so therefore this is the inverse of this, and this is the inverse of this. Okay, let's move on to theorem 6. Which says, let A be equal to the matrix A, B, C, and D. Now the determinant of A, then det of A is equal to the product of the diagonal elements, so AD minus BC. And if det of A is non-zero, then A inverse exists and is given by 1 on the determinant, so that's AD minus BC, multiplied by the matrix, obtained by swapping the diagonal elements and putting minus signs in front of the other elements, or D minus B minus C, A. Okay, so to see that this holds, let's multiply A times A inverse. So we have A, B, C, D multiplied by 1 on AD minus BC times D minus B minus C and A. Okay, now this out the front, that's a scalar. Since the determinant's non-zero, this is a number, so we can move this out the front. and then multiply this by this, and so we get A times D minus B times C. Okay, next, this row times this column gives us minus AB plus BA, which is AB. And next, this row times this column, okay, we have CD, and then minus CD. And then we have this times this, so that's minus BC plus AD. Okay, and so this is the same as this. So if I divide this in, I get 1. So I have 1 there. Now this is 0, so I have 0 over this, which is 0. And then this is 0, so we have 0 there again. This is the same as this denominator, so we have 1. And that's the identity matrix. Alright, now if you do this the other way around, you'll get the same thing, the identity matrix. So, I'll leave that part to you, and let's move on to example 7.3. So we've got a matrix A equal to 2 minus 3, 4 minus 7. And the question says find A inverse if it exists. Okay, so let's work out whether it exists first by taking the determinant. So det of A is equal to the product of the diagonal elements subtract the product of the off diagonal elements. So minus 14 subtract minus 12, which is equal to minus 14 plus 12, and that's minus 2. Okay, so yes, it exists. So hence, A inverse exists because this is non-zero. Okay, and we can find it. A inverse is equal to 1 over the determinant of A, so 1 over minus 2. And then remember, we swap the diagonal elements and put minus signs in front of the off diagonal elements. Alright, so there is our inverse. And now if you want to, you can even take this minus 1/2 inside, and we'll call that 7 over 2 minus 3/2. This is minus 2, and this is minus 1. Okay, so I would say it doesn't matter which way you leave it. I personally prefer this way, with the unfortunate looking fraction out the front rather than in every entry, because there's less writing. Alright, and then you can easily verify that A inverse equals I, which is equal to A inverse times A. Now there's a formula for the inverse of a 3 by 3 when the determinant's non-zero, but as you get bigger in size, so n by n, where n is, say, bigger than 3, it's not really practical to use a formula for the inverse of an n by n. Okay, but the determinant of a 3 by 3, so the determinant of A, B, C, D, E, F, G, H, I is equal to AEI minus AFH minus BDI plus BFG plus CDH minus CEG. But you can work this out yourself because you know how to calculate the determinant of a 3 by 3 matrix, right? So, for example, if you factorize the A out of this first piece, you see that this is the determinant of EFHI. Okay? So you know how to do that. Now, the inverse of a 3 by 3 is 1 over the determinant of A multiplied by the 3 by 3 matrix that has determinants in every entry. Okay, and those are EI minus FH, CH minus BI, BF minus CE, and so on, right? So those are determinants. But if I show you what those are, okay, so let's perhaps show you what those are as determinants. So what do we have here? This is the determinant of E, F, H, I, which is the matrix right there. Okay, next we have C. Let me think about this. So the determinant of, it's actually minus the determinant of B, C, H, I. Yes, okay, then next we've got the determinant B, C, E, F. So you can get these by crossing out certain rows and columns of the original matrix. Alright, now below that we have FG minus DI. So this would be minus the determinant D, F, G, I. Alright, next we would have AI minus CG, so that's the determinant AC, GI. And then next we have CD, CD minus AF. Okay, so let me be careful about this. That's AC here and a minus in front, and then DF. Okay, down here we've got another determinant DE, GH. And then here we have minus a determinant AB, GH. And then here we have a determinant AB, DE. Alright, so this 3 by 3 matrix determinant is made up of several 2 by 2 determinants. Alright, let's move on. Okay, an important identity for the inverse of a square matrix, n by n matrix, is the following. So if A and B are invertible n by n matrices, meaning, equivalently that their determinants are non-zero, then the inverse of the product of A and B, specifically AB inverse, is B inverse A inverse. Now there's a typo in the notes, so this should say A inverse, not A to the power 1. Okay, so to see that this holds, let's multiply out AB times B inverse A inverse, right? Because if this gives the identity, then that would say that the inverse of this matrix is the inverse of, or AB is the inverse of this matrix, okay? So now associativity of matrix multiplication allows us to express this as A, B inverse times A inverse, right? Because with associativity, you can move your brackets around provided you don't change the order, the left-right order. Okay, now B inverse is the inverse of B. So we've got A times I times A inverse, which is A times A inverse, and that's equal to I. Okay, so we've shown that this times this gives the identity matrix. Now the other way around, B inverse A inverse times AB is equal to B inverse A inverse A, moving the brackets around by associativity. So we've got B inverse I B, which is B inverse times B, which is I. So again, the product of those two gives the identity matrix, and hence the result follows that A B inverse is equal to B inverse A inverse, which is a pretty nice result. Alright, so now let's discuss Gaussian elimination to calculate a matrix inverse. And this is a better process than solving a matrix equation using the inverse, because it's probably more efficient. Okay, so Gaussian elimination is a process of row reduction due to Gauss-Jordan to convert a matrix into what we call a row-reduced echelon form, or RREF. We use valid row operations on a matrix to do this. These are listed as follows. We can multiply or divide a given row, by some non-zero k, or some non-zero number. Okay, so that's one operation that's valid. We can swap rows. We can replace a row with a linear combination of two other rows, or a sum of scalar multiples. Of two other rows. Okay, so these two here are covered by the third one, right? Because if we're replacing, say, the first row with 2 times the first row, well, then what we've done is really the third one. We've replaced a row with a sum of scalar multiples of 2 other rows. Well, the scalar multiples would be 2 and 0, and the 2 other rows would be that first row itself and some other row. Okay, so this is really all you need. So I'll just put a double asterisk for that one, because that's the key rule to remember when it comes to valid row operations to perform Gaussian elimination. Alright, so when we do that, when we have performed a row operation on a matrix, we use this symbol, a tilde, to say that they're equivalent under row operations, right? The corresponding system of equations that they represent is the same. All Alright, let's have a look at definition 1 here. A matrix is in row reduced echelon form if the following 4 conditions hold. Okay, I'm going to rewrite that here. So definition, A is in row reduced echelon form if the following conditions hold. Okay, and the first one is all rows that are all zeros are at the bottom. Okay, I've written bottom over here on the right hand side, the bottom of the matrix. So all rows, if any, consisting entirely of zeros appear at the bottom of the matrix. Okay, second condition, the first non-zero number starting from the left in any row not consisting entirely of zeros is 1. So first non-zero number from the left in any non-zero row is a 1. Alright, so the third thing that we require for this matrix to be in row reduced echelon form is if 2 successive rows do not consist of all zeros, then the first one in the lower row occurs farther to the right than the first one in the higher row. And you probably need an example of this. Okay, so let's do that. So 1 0 1 0 0 for example, and then underneath that we've got 0 0 1 0 2, and then below that 0 0 0 1 0. Okay, so for example this satisfies that condition because our leading ones, okay, so these two don't consist of all zeros, then the first row left to the first one left to right, which is here, this we call a pivot, it's farther to the right than this, and this is farther to the right than this. So that's what we're referring to there. Okay, now last condition that needs to be met in order for the matrix to be called in row reduced echelon form is any column containing the first one in a row has zeros everywhere else, meaning below it. Okay, so we need to have zeros below the pivots. Alright, and you can even go so far as to have zeros above your pivots as well. But that's a little bit more than row reduced echelon form, if I remember my definitions correctly. Alright, so oh, no, I'm misunderstanding that. Okay, sorry. Okay, in any column containing the first one in a row, it has zeros everywhere else, so not just below it. That's the property I'm talking about. So this one is not in row reduced echelon form, but it does satisfy condition 3. Okay, so this one, so not below it, we'll say everywhere else. Right, and so let's just give an example of that by modifying this matrix somewhat. So we have 1, 0, let's see, I'm going to subtract row 2 from row 1. So 0, 0, then we would have minus 2. Then next we'd have 0, 0, 1, 0, 2, and 0, 0, 0, 1, and 0. So this matrix here satisfies all 4 of those properties. So this matrix is in row reduced echelon form. However, if you only have conditions 1, 2, and 3, then you can just call it in row echelon form, not row reduced echelon form. So this matrix here is in row echelon form. So only one R in that acronym. Alright, let's have a look at how we would perform Gaussian elimination on a simple example. Okay, so what we do is we start with now this will be to use Gaussian elimination to find the inverse of a matrix A. So we would start with A concatenated with the identity matrix I to use Gaussian elimination to find A inverse. Now remember, for 2 by 2 and 3 by 3 matrices, we had simple enough formulas for the inverse. So while we can use this technique on 2 by 2 and 3 by 3 matrices, it's possibly best used on 4 by 4, 5 by 5, and slightly higher order matrices, because we've got simple formulas for the inverse of a 2 by 2 and the inverse of a 3 by 3. Although you can argue that the inverse of a 3 by 3 is not all that simple, as you've seen. Okay, so let's have a look at an example here, which is example 7.4. We've got a matrix A equal to 2 minus 3, 4 minus 7. And hey, we already know how to calculate the inverse of this, but the question here says use Gaussian elimination to get A inverse, alright? But let's just verify. Now our determinant is 1 over minus 2. I think we've already calculated this. So let's just say we know from before, from an earlier example, that A inverse is equal to minus a half outside of minus 7, 2, 3, and minus 4. Okay, so we already know this from a previous example. So now what we're going to do is use Gaussian elimination to get the same thing. Okay, so we put in our matrix 2 minus 3, 4 minus 7, and next to that we concatenate the identity matrix 1, 0, 0, 1. And now we're going to perform row operations on this until we get... So back to this statement. So we use Gaussian elimination on this to find this by row reducing until we get identity concatenated with A inverse. Okay, so that's what we're doing here. All right, so now what we might want to do first is, now what I like to do, which is slightly different than what Lauren does sometimes, is I like to multiply a given row and then take a difference, right? So in the way that I like to do it, I avoid fractions until the very end. But if you prefer to do that by, forming your pivots first, that's totally fine too. All right, so now in the way that I would do this, I would say, all right, I'm putting the tilde to say that these, I've done a row operation here. Now what I'm going to do first is multiply row 1 by 4, or sorry, by 2, so that we get 4. So that's row 1 multiplied by 2. Okay, where this is row 1, this is row 2. So multiplying that by 2, we've got 4 minus 6, 2, 0. And then under that, we have the same as we had before. Okay, and this is just R2. All right, next I want to take the difference. So in other words, I want to replace row 2 with the difference of the 2. So that would be 0. Now, minus 6 minus 7 is 1. 2 minus 0 is 2. 0 minus 1 is minus 1. And then, at the same time, I want to take this back to its original form, which is just to divide this by 2. So 2 minus 3, 1, and 0. Okay, so row 2 was row 1 minus row 2, and row 1 is half row 1. Okay, so next I want to use this pivot I've got here to get rid of the 0 above it. Get rid of the number above it and make it 0. So that's what I'll do next. I'll multiply this by 3, second row by 3. So 3 times row 2, that's just the same. Okay, and then I want to add, so I'll come over here now, and so adding, I'm replacing row 1 with the sum of the 2 rows. And then I'll replace row 2 with 1/3. So I get back what I started with. Okay, so that's 1/3 row 2, and this one was the sum of the 2 rows. So R1 plus R2. All right, so we nearly have the identity there on the left. Now all that remains is to divide row 1 by 2. So we get 1, 0, 7 halves, minus 3 halves, and 0, 1, 2, minus 1. So this is 1/2 of row 1, and this is just row 2. And so this is identity followed by A inverse. And so we get that A inverse equals 7 halves minus 3 halves, 2, and minus 1. All right, let's move on to another example. So this example says, attempt to find the inverse of the matrix 3, 2, 6, 4. And I've got to get the focus fixed. There we go. So attempt to find this. Okay, so what we'll do is we'll set up AI so we've got 3, 2, 6, 4 identity matrix. Alright, so we'll start to perform row operations. So let's multiply row 1 by 2. We've got 6, 4, 2, 0, then 6, 4, 0, 1. So that's 2 times row 1. This is row 2. Okay, now clearly we can replace row 2 with the difference of row 1 minus row 2. So we would have 0, 0, 2 minus 1. So that's row 1 minus row 2. And then this we can replace to its original form, which would be 1/2 of row 1. Okay, now we can see already that it's impossible to form the identity matrix on the left here, right? But let's go ahead and continue to put this in row-reduced echelon form. Okay, so what we want to do now is just divide row 1 by 3. So we have 1, 2/3, 1/3, 0, and then divide row 2 by 2. And so what have we done? We've done 1/3 row 1 and 1/2 row 2. And now this is in, oh, not quite, is it? It's not quite in that. So hang on, I've got one more thing to do. So really I would have to multiply this by 1/3, but I should have just dealt with the integers and then subtract. And so I'll say this is equivalent to 1 2/3, 0 1/6, 0 0 1 minus 1/2. Okay, so this now is in row reduced echelon form, but we can see a problem if our task was to find the inverse of A, because we cannot possibly get the identity on the left, so not the same as identity A inverse. So we can conclude from that that A inverse does not exist, DNE for short. Alright, now you can also see that the determinant of the original matrix is 0. Right, so that's pretty conclusive. Okay, next example. Let's find the inverse of the matrix 6, 5, 5, 4 if it exists. Using Gaussian elimination, but we already know, I think, because we've been using this before. Okay, let's just calculate it again. But we'll say we know, because it's easy to calculate, that A inverse is equal to, now the determinant of this is 6 times 4 is 24, minus 25 is minus 1. So 1 over minus 1, swap these, put minus signs on these, and then let's simplify because it's just minus 1. So we've got minus 4, 5, 5, minus 6. So this is supposed to be the inverse. This is what we're supposed to get in the end. So we're doing this by Gaussian elimination. Okay, so we set up the matrix A concatenated with I. And we row reduce. So multiply the top row by 5, because there's a 5 there. So 5 times 5 is 25, 5 and 0. I'll multiply the bottom row by 6 so we can get 30 there. 6 times 4 is 24. Okay, and so this is 5 by row 1. This is 6 by row 2. Now I'm going to take a difference, replacing row 2 with row 1 minus row 2. So we'll have 0, 1, 5, minus 6. And then now we can replace row 1 with 1/5 of row 1. Dividing by 5, we've got 6, 5, 1, 0. In other words, what we had originally there. Okay, next what we want to do is use that 5 there to eliminate the 5 above it so we can satisfy condition 4 of row reduced echelon form. Okay, so I'll multiply this by 5 and then subtract. So now it's ready to subtract. So 6, 0, minus 24, and that's plus 30, isn't it? Minus 30. And this is row 1 minus row 2. Now with the second row we can divide by 5 and put 1, 5, minus 6, and that would be 1/5 row 2. Now I can see here everything is divisible by 6, so this is easy. We have 1, 0, minus 4, and 5, and then 0, 1, 5, minus 6. Okay, so what we have done is multiplied row 1 by 1/6 and left our 2 the same. Alright, so that's in row reduced echelon form. We can see that we have the identity on the left. So A inversed, we just read it off of this. It's minus 4, 5, 5, minus 6. Okay, and that agrees with what we calculated using the formula for the inverse of a 2 by 2 matrix there. Alright, so let's move on to example 7.7, which is our last example of this video. In which we're going to use Gaussian elimination to find the inverse of a 3 by 3. Now remember, we have a formula for this, but it's not all that simple. So it's hard to say which one is more work. Alright, so we've got a matrix A equal to 1, 2, minus 1, 3, 5, minus 1, minus 2, 1, minus 2, and we need to set up A concatenated with the 3 by 3 identity matrix I. So we're going to write down 18 entries You want to make sure you copy this down correctly. Here I put the identity matrix on the right. Okay, and then we start to perform row reduction on this. So the first thing I want to do is multiply the top row by 2, so then I can add it to the third row and put a 0 under that pivot there. So that'll be 2, 4 minus 2, 2, 0, 0. And that's row 1 by 2. Copy down the second row the same. And then the third row the same as well. And this should be tilde, not an equals. Okay, now we want to add row 1 to row 2, so we're replacing, or row 3, we're replacing row 3 with row 1 plus row 3. So that'll be 0, 5, minus 4, 2, 0, 1. Okay, and then everything else the same, except for now I can divide row 1 by 2, and in fact let's multiply that by 3 while we're at it. So I'm going to multiply row 1 by 3 over 2. So I get rid of the 2's that I've put there, and I get a 3 so I can do something with the second row. So that will be 3, and then the 4 over 2 is 2 times 3 gives 6, then minus 3, 3, 0, and 0. Okay, now row 2 should be just the same. Okay, next we want to take a difference between row 1 and row 2. So let's take replacing row 2 with row 1 minus row 2. We'll leave row 3 just the same, and then we'll divide row 1 by 3. Okay, so let's see, dividing row 1 by 3, we have 1, 2, minus 1, 1, 0, 0, just as we have up here. Now, row 1 minus row 2, that gives 0, 1. Minus 3 minus minus 1 is minus 2. 3 minus 0 is 3. 0 minus 1 is minus 1. 0 minus 0 is 0, and then row 3 just the same. Okay, so now we've placed a pivot there, 0 is under the pivot. That's good. Next we want a pivot here, if possible. So we need zeros above and below that number 1 there. Okay, so what I want to do now is replace row 3 with, let's see, 5 times row 1 minus row 3, so that we get a 0 down here. Alright, so 5 times 5 minus 5 is 0, so 0, 0. Okay, 5 times minus 2 is minus 10. Take minus minus 4, or take minus 4. So that should give us, oh, hang on. That should give us 6, or minus 6, isn't it? Yeah, it gives us minus 6. Okay, then 3 times 5 is 15, minus 2 is 13. 5 times minus 1 is minus 5. Take 0 is minus 5. 5 times 0 is 0, minus 1 is minus 1. Okay, great. And then I'll copy everything else down the same. Okay, so need more paper now. So next we can clearly multiply this by row 3 by minus 1. Can we do anything else at the same time? Well, we can make it possible to subtract, get rid of this 2 right there. So let's go ahead and also multiply row 2 by 2. And then just taking the negative of the third row. 6, minus 13, 5, and 1. Okay, so now that we have a 2 there and a 2 there, we can take the difference. In other words, we can replace row 1 with row 1 minus row 2. And so we'll have 1, 0, minus 1, minus 4 is 4, minus 1 is 3, 1 minus 6 is minus 5, 0 minus 2 is 2, and 0 minus 0 is 0. Okay, next I want to divide row 2 by 2 to make it just the same as there. So 0, 1, minus 2, 3, minus 1, 0. And then row 3 just the same. Okay, great. So continuing, what we want to do next, since we've got a pivot here, zeros are everywhere else, we've got a pivot here, zeros are above and below it. We want to have a pivot here and then get rid of the numbers above it by subtracting. So let's actually do that first. Let's put zeros above it. So we're going to add row 3 to say minus 2 times row 1 and something similar, or sorry, row 2 and then something similar for row 1. Alright, so let's do that. We'll replace row 1 with twice row 1 plus row 3. Okay, so that we get a 0 there. So then we'll have 1, 0, 0, twice minus 5 is minus 10, plus 13 is 3, twice 2 is 4, plus minus 5 is minus 1, twice 0 is 0, plus minus 1 is minus 1. I feel like there maybe is a mistake here. Is there a mistake? Better double check because my notes don't quite say the same thing. And it's a pretty tricky process. Oh yeah, we multiplied this by, so that should be a 2 there. Great, okay, that was easily found. So next I want to replace row 2 with, let's see, so how about minus 3 row 1 plus row 3, so that we would get a 0 there. Okay, so minus 3 times, oh sorry, that's row 2, isn't it? Row 2. Minus 3 times row 2 plus row 3. Okay, so we would have 0 minus 3. Now, minus 3 times minus 2 is 6, plus minus 6 is 0. Minus 3 times 3 is minus 9, plus 13 gives us 4. Okay, then minus 3 times minus 1 is 3, then plus minus 5 gives us minus 2, and then minus 3 times 0 is 0, then minus 1 is minus 1. Okay, and then row 3 just the same. So we're nearly there because we've got zeros above and below our pivots. We just have to divide by the appropriate number, so we have 1, 0, 0, so that we have the identity on the left, right? So that's easy now. So we divide row 1 by 2, so 1/2 row 1. This will be minus 1/3 row 2, and then minus 1/6 row 3. Okay, so this gives 1, 0, 0, 3 halves, minus 1/2, minus 1/2. Alright, next we're going to divide by minus 3. So we've got 0, 1, 0, minus 4/3, 2/3, 1/3. Ooh, is this correct? Is this correct? That doesn't quite agree with my notes there. My notes say I should have a 0 here. Okay, let's double check. What have we done? Multiplied by minus 3, added to this. That looks right to me. Okay. Alright, so then we're taking this last row and dividing by minus 6. So we'd have 0, 0, 1, minus 13 on 6, 5 on 6, and 1 on 6. Okay, I'm going to get the computer to check my inverse here.